We're going to start off today with an animation. And as you watch, we invite you to think, has this happened to you before?
Hey, Google Maps, can you tell me how to get to my destination? Oh, for sure. All right, so getting to that destination from your current location will take 26 minutes. Cool, thanks. Also, there's a dirt road coming up that's 5 minutes faster. But if you wanted to take the Wait, did you just say faster? Yeah. That way will get me to my destination faster. Sure will.
And you're sure it's faster?
Mm-hmm. Huh. Well, thanks, Google Maps. You've actually made a useful suggestion.
Our key takeaway from this is you can't give everybody the best route. If everybody is suddenly given the same best route, then really, nobody has the best route. So let's take a look at how this happens again. If Daryl, Carl, and Betty try to take the same best route, everybody goes to the same place, leading to traffic jams, and nobody's happy. And something similar happens on the internet. If we replace the cars with data and the traffic lights with internet routers, and lots of data wants to take the same path, this leads to internet congestion, the internet version of a traffic jam. This is caused because, like Google Maps, the internet usually routes data on the shortest path. So we really need better routing.
So as Jonathan said, just as we have the problem of routing cars at a traffic intersection, we have the same problem when it comes to routing data on the internet, except it's much, much bigger. Now, just for some perspective, in 2024, we generated over 100 zettabytes of data. That's zettabytes with a Z. That's a 1 followed by 23 zeros. And of that data, we spent around $55 billion to route just 25 zettabytes. For context, Google, one of the biggest data and internet companies on the planet, in total has around 0.15 zettabytes of data across all of their servers, infrastructure, everything. So in 2024, in effect, we've routed over 1,600 Google's worth of data. And just looking at the trend from the past couple of years, we only expect this figure to grow faster and faster, with us projected to hit nearly 200 zettabytes in 2025. But not only is the sheer volume of data that we're producing, streaming, and consuming increasing more and more, it's also the number of ways in which we're using it. Gone are the days where looking at static HTML or websites are the only ways we consume data on the internet. In fact, the way we use the internet today is a lot different. It looks something like video streaming. In fact, most of the internet's data today is in the form of video, around 80%. Just looking at YouTube alone has 720,000 hours of video uploaded to the site every single day. We've seen the rise of IoT, or Internet of Things, and smart devices. Gone are the days where you have to use a desktop computer to access the internet. And in fact, the internet is embedded in everything all around us, from our smartphones to cameras to sensors, everywhere. And all of those devices means generating a huge amount of data. By the time we hit 2030, we're projected to have up to 29.4 billion IoT connected devices. And more recently, we've seen the rise of AI and LLMs, such as ChatGPT. Each query that you plug into ChatGPT or Claude or take your pick, it involves streaming hundreds or thousands of these tokens or billions of inferences worth of data over the internet continuously just to serve a single request. And companies that deploying these LLMs are collectively investing tens of billions of dollars just into networking infrastructure to meet this incredible demand. So what does this mean? We've seen all these incredible ways that the way we generate and use data has improved. In other words, how we compute with data. But our networking still struggles to keep up. We still route data more or less the same way. So while our computing has gotten better, our networking, and importantly, routing, hasn't. So for the future of a more interconnected world, we need better routing.
So what does better routing look like? Well, we can dive into what makes a smart routing decision by going back to the traffic analogy. Our traffic lights follow simple cycles which allow cars to pass in different directions. But imagine if the traffic light could be smarter and know which car is in front of it and which car needs to get somewhere the fastest. For example, if an ambulance and Carl, late for his final exam, arrive to alight at the same time, who should be allowed through first? while most people would say the ambulance. This was a trick question because the right answer was Carl. What if we told you that the ambulance isn't on duty and doesn't have a patient? In this case, it doesn't need to get through the light very quickly, but Carl does. And all of this is to illustrate that a lot of factors go into making a smart routing decision, and they end up being very complex.
So now we know that if we simply send data down the shortest path, this leads to internet congestion. But let's consider what it would take for us to make smarter decisions with data routing with current internet infrastructure. Currently, data has to jump through many hoops to get to its final destination. It has to go through the router hardware to be processed first, and then move to the routing software where wasteful packet transfer is used. This slows things down. Then bloated software has to make a decision, causing higher latencies. Finally, the data can then be forwarded back to the router hardware, where again there is a wasteful packet transfer, and then forwarded to its final destination. This is way too slow to keep up with the amount of data on the internet, which is why it isn't done in practice. We need a better solution. We need the Smart Switch, or S2 for short. The S2 gets rid of the wasteful packet transfers and the slow, bloated router software. We introduce a neural chip that makes smart decisions on the router itself, allowing for faster transfer of data between the client and server. This solution avoids congestion and improves quality of service.
So that's our product, our S2. But what does the rest of the industry look like? We took a look at 3 flagship products in the industry. You might have heard some of these. We have NVIDIA's Bluefield DPU, designed for networking for data centers. We have Xilinx Alveo SmartNICs, and we have Intel Tofino's programmable switch. All of these are flagship state-of-the-art products in the industry, designed for large-scale industrial data centers. And while that's great and all, that's exactly the problem. They're designed for industrial data centers. And what does that mean? That means they're expensive. Just looking at the price of some of these units, they command a single DPU or a NIC or a switch commands upwards of $4,000, $5,000, even over $10,000 in the case of Intel. And not only are they more expensive, they can't do what we do. We are the first to enter this market with fully integrated hardware smart routing. NVIDIA's Bluefield DPU and Intel switch only does basic header matching, and the SmartNIC from Xilinx, while technically possible to do content-based smart routing, it requires a lot of effort from the consumer and knowledge of hardware design. And so while all of these are different ways of hardware-accelerated networking, S2 is the first one to take a smarter, cheaper approach, and we do all the hard work for you out of the box. So while we're talking money, let's talk money. The market for potential for S2 is huge, and we break it down to you in 3 key metrics. We have our total addressable market, which is the total maximum theoretical market we can address with this sort of product. We have the service addressable market, which is the portion of the market we hope to reasonably be able to address within 3 to 5 years. And we have the service obtainable market, which is the precise niche that we're targeting and we realistically expect to capture within a couple years. So looking at the total addressable market, or TAM, we're looking at all networking infrastructure, which is an $143 billion market. Within that, we're looking at specifically networking infrastructure for edge AI and IoT, and that subset makes up around $28 billion. Now, assuming we can just penetrate just 1% of this market, targeting mid-sized system integrators and or system service providers and OEMs that might not have sophisticated network infrastructure, we're looking at $280 million of revenue within the next few years, assuming just a 1% capture rate.
In our current setup, we implement a software router on the NetFPGA platform to perform content-aware routing based on digit classification. Incoming packets contain image data representing handwritten digits. This data is processed by an integrated model which predicts the digit encoded in each image. Based on the prediction result, the packet is forwarded to a designated node. Digits 0 and 2 are routed to node 1, digits 4 and 6 are routed to node 2, digits 7 and 8 are routed to node 3. Packets corresponding to other digits are dropped by the router. This setup demonstrates an intelligent routing mechanism that leverages on-the-fly inference to direct traffic according to data content rather than fixed destination addresses. This demo illustrates how AI-assisted routing can support load-balanced network systems. In our setup, the software router on the NetFPGA node acts not only as a traditional packet forwarder, but also as a classifier that determines how traffic should be distributed across available servers, in this case, nodes 1, 2, and 3. By analyzing the content of packets, specifically digit images, we simulate an application-aware network where routing decisions are based on deeper packet inspection. This mechanism reflects real-world load balancing where traffic is distributed based on application layer attributes such as HTTP headers, content type, or user behavior. In our case, digits like 0, 2, 4, 6, and 7 were routed correctly here, demonstrating effective distribution across backend nodes. However, the misclassification of digit 8 as 0, resulting in its redirection to node 1, illustrates how imperfect decisions can impact performance. The measured throughput was just 0.126 megabits per second, which is far below the demands of practical load balancing systems. This underscores the need for hardware-accelerated and optimized implementations to achieve higher throughput and reliability.
Thank you, Edwin, for that lovely, lovely demo. Now, with that being said, let's get to the secret sauce of how everything works, the hardware. At a high level, our design works like this. We have network data come in on the left side that then gets stored temporarily within a network FIFO. We have our custom neural chip that runs our classifier model that inspects within the content of each packet and is able to semantically predict what type of traffic we're looking at and thus where to route the output. So a lot of the secret implementation, or the secret sauce, if you will, comes within this neural chip. So let's take a deeper look. At a high level, we run a 3-layer classifier model where we have 64-bit inputs, which are then expanded to FP16 or fixed point 16 format that represent the content or payload of each of our individual packets. And within there, we have a 16-node hidden layer followed by a 10-node output, or 10 different classifications we can run. So this is the architecture of our simple ANN, or artificial neural network. And so given a 64-bit input, we are able to classify it into one of 10 possible outputs that we can then route it to. Now, to do this efficiently, we need to perform a lot of inference, which means a lot of compute. So leveraging hardware primitives on the FPGA combined with our own custom design, we were able to implement 2 highly efficient MAC cores. So each of these are responsible for doing a lot of the number crunching when it comes to computing the activations for our model. And so with each of these cores computing 1 neuron activation per cycle, and each inference taking around 50 cycles with a targeted clock rate of 125 megahertz for that FPGA, this means we can process up to 2.5 million inferences per second, which puts us well above the line rate of the NetFPGA considering packet sizes. This is the miracle of S2, and this is what is not possible in software.
And let's take a closer look at the components which make the S2 system possible. We have already discussed the neural chip, which is at the heart of it all, allowing us to run inferences on packet contents. But how is it programmed? Well, it all starts from the artificial neural network defined in a standard framework such as PyTorch. This can be converted into a weights text file by software that comes packaged with the S2. This software enables any programmer to simply use the machine learning framework they are comfortable with. A weights file is a program for an S2 and can be used to directly program the neural chip. Neural chip inference produces logits, which are processed by a max decoder module to determine the classification of the packet. And from this classification, a packet modifier module outputs the proper control signals to modify a packet, for example, by changing its destination and checksum, to ultimately make a routing decision.
Here, we demonstrate the performance of our hardware router using the same setup as the software-based implementation, but with routing now handled in hardware. As shown, digits are correctly routed to their respective nodes based on the predicted digit. The measured throughput of our hardware design reached 86.486 megabits per second, a significant improvement over the software router, and much closer to the performance expected in real-world load balancing systems.
So what did we learn today? We learned network routing is a huge problem. In fact, it's a multi-billion-dollar problem. And just when it comes to the beginning of today, when we learned with Google Maps that you can't give everyone the best route when it comes to traffic, you can't give everyone the best route on the internet. And what does that mean? That means our existing routing isn't cutting it. We can't imagine the ambulance the same as the student driver. And so we need, as network demand and traffic increases more and more, we need to alter the way that we make intelligent routing decisions on the internet. But with S2, we offer a smarter solution for the future of the internet, a future built on smarter, better routing, entirely in hardware. My name is Eric. I'm joined today by my amazing teammates Edwin and Jonathan, and we are Team S2, and we are seeking to reimagine the traffic light of the internet. Thank you very, very much. I'll be happy to answer any questions.